Okay, we have 1363 here, and we have this pendulum here with bob B here, and we know the weight of the bob is 5 pounds, and we know that the radius here from B to C is 3 feet. And what this problem is trying to find is the tension in BC, so the tension connecting this pendulum to its pen joint here at two places, when theta is equal to 0 degrees, so right up top here, and then also when theta is equal to 45 degrees. So um, those are the two things that we're looking to find. So let's tackle this 0 degrees first. And let's just draw a free body diagram at 0 degrees. We have the bob here. We're going to have uh, tension just in this horizontal direction. Let's see if I can draw that. So we have tension going this direction, and then straight down we have mg, the weight of the bob, which we know is 5 pounds. So, and if we want to talk about normal direction and tangential direction, we can, make a coordinate system such as this, where this is t, the tangential direction, and this direction here is normal direction. So let's sum the forces in the normal direction, and that should be equal to the mass times the acceleration in the normal direction. So doing this situation here, we have the forces in the normal direction, which is this direction. We have just T, and T is equal to the mass of the bob, and we know the weight of the bob is 5 pounds, but if we take that divided by 32.2 feet per second squared, that should give us the mass. And then we have the acceleration in the normal direction here. Now, if we know this bob starts out from rest, remember that there is a relationship between the normal acceleration and the velocity, right? So we have an is equal to the velocity squared over rho here, where rho is kind of the radius of curvature. All right? We know the radius here is 3, but since it starts out from rest at 0 degrees, we know the velocity is actually 0. All right, so that comes out the acceleration in the normal direction, 0. So we end up getting the tension is just equal to 0 at theta equal to 0 degrees. Okay, so let's move on to the more complicated case when theta equals 45 degrees. So this was when theta is equal to 0 degrees. Let's move on to the case when theta is equal to 45 degrees. All right, I'm going to start out by drawing a free body diagram again. So we have the bob here. I'm going to have a tension there, and then we have m times g downward here. And this direction here is the normal direction. And then this direction here will be the tangential direction. Right? So let's just sum the forces in the tangential direction. And that should equal the mass times the acceleration in the tangential direction. So in the tangential direction here, this angle is actually theta, which is equal to 45 in our case. So we have m times g, which is 5 pounds, cosine theta, right? That would be the projection onto this tangential axis here, equals the mass, which is 5 divided by 32.2, times the acceleration in the tangential direction. All right, and here we get the acceleration in the tangential direction is equal to, the 5's cancel out here, is equal to 32.2 cosine of theta. Okay. So let's continue on by taking the sum of the forces in the normal direction and setting that equal to the mass times the acceleration in the normal direction. So the normal direction is this way. So we have t pointed directly in the normal direction. So we have t. And then we'll have a component of this mg, and that component will be acting in this direction. So that's minus mg sine of theta, and that should be equal to the mass times the acceleration in the normal direction. We know m times g here is equal to 5 pounds, so let's just sub stuff in here. So t minus 5 sine, and we know theta is 45 degrees, equal to the mass, which is 5 divided by 32.2 times the acceleration in the normal direction. Now, remember what our equation is for the acceleration in the normal direction, right? This is equal to the velocity squared over rho. And we know rho is 3 meters, but we don't know the velocity when theta is equal to 45 degrees. So to be able to solve for the tension at 45 degrees, the tension in this cable, we need to know the velocity. Luckily, the velocity is somehow related to the tangential acceleration. So if we know the tangential acceleration, basically in this direction, how fast we're accelerating there from rest, we can figure out the velocity, and then once we have the velocity, we can solve for the tension. So let's continue on this path. And if you remember this equation, v dv is equal to a ds. All right. So we could set this v dv is equal to the acceleration in the tangential direction ds. All right. So what is this differential element ds here? Well, if we take a look at the bob just hanging, all right, we have the bob here, just a small differential element this direction is ds, all right, that's this small little bit here, and this angle here is then d theta, just a little bit of theta, and we know the length of this from where it's attached to the bob is 3. So if we relate these two together, we know ds is equal to 3 times d theta. So d theta is here, that's that angle there. And we multiply those two together and we figure out this distance here. So we can sub that in. So now we have v dv equals tangential acceleration, and we're subbing in for ds. ds is now equal to 3 times d theta. Okay. And we do know the acceleration in the tangential direction, right? It's 32.2 cosine theta. So let's put that in too. So again, we have dvd, and the acceleration is 32.2 cosine theta, that times 3 d theta. Now we have this in a position where we can integrate this. We can integrate both sides. So we'll integrate the left side from rest, from a velocity of 0 to v. So we have v dv on the left-hand side. And there are a lot of constants here. So I'm going to bring 32.2 out front because that's a constant, and 3 out front as well. So we'll have 32.2 out front of the integral here. And then we have the integral here from 0 to 45 degrees, and that is cosine theta d theta. All right, let's keep going. Right, if we integrate the left-hand side, that is just v squared over 2. And the right-hand side, remember that the antiderivative cosine theta is sine theta here. So we have 3 times 32.2 sine theta. And sine theta is evaluated from 0 to 45 degrees. And if we plug everything in, this right-hand side then comes out to be 68.3065. And if we solve for v squared now, so v squared comes out to be 136.61 feet squared second squared, right? And now that we know this, we can plug this back into this equation here. So we have v squared, we can plug that in here, and then we can go back to solving this equation. So we know v squared, we know rho here, we can plug that in for the acceleration in the normal direction, and then all we need to do is solve for t, and t comes out to be 10.6 pounds. And that is our answer for 1363.